Hello and welcome to Inside Exercise. I'm Emeritus Professor Glenn McConell from Victoria University in Australia. Today I'm bringing to you Professor Niels Ørtenblad from the University of Southern Denmark in Odense. He's an expert on muscle glycogen, and we talk today about why is muscle glycogen important. You'll see that muscle glycogen is indeed very important. So as long as you're exercising an intensity above like a low intensity where you can get away with burning fat, as you increase the intensity, you need to rely more and more on carbohydrate, and that carbohydrate is becoming more and more from glycogen. And indeed, glycogen can play a role in fatigue. So if you're doing prolonged exercise, the muscle glycogen can become depleting, and at that point, it may contribute to fatigue. So we talked a lot about this. Does muscle glycogen play a role in fatigue? How do we know that? How's it been studied? What about different intensities and durations of exercise? What about if you ingest carbohydrate? What's the effect of whether you're endurance trained or not? So you're sparing muscle glycogen during exercise. If you're endurance trained, you don't use it as quickly. Does it get depleted mainly in slow or fast fibers? What effect does the depletion have on muscle contraction, force, etc.? So, very interesting chat. So stick around. I think you'll learn a lot. Hi, Niels. How are you? Welcome to Inside Exercise. Thank you for coming on.
Thanks for inviting me. Thank you.
Some of the people listening to this may know that I've been very lucky to have spent over a year in Copenhagen on various sabbaticals and things. And indeed, actually, I don't know if you know, I'm coming back in a couple of months, another 6 months. Oh, and yes, now what I was going to say was, it's very hard sometimes to pronounce Danish things. So I say Niels Ørtenblad. How do you say your name?
Well, that's perfect in English, but in Danish, Swedish, Norwegian will be Ørtenblad, which is hard to pronounce.
Yes, and I did struggle a little bit over there. I learned,
and I got this ridiculous letter with Ø. It's actually an O-E. Yeah.
And also, I went to give a talk at your, University of Southern Denmark, which was great. But when I tried to organize it with the administrative person, she had no idea what I was talking about when I said, when I get the train to Odense, she's like, what? So O-D-E-N-S-E. O-D-E-N-S-E. How do you say that?
It's just do it flat. Odense, we say in Danish.
Odense, yes. So I was proud that I kind of learned how to say Odense. Yeah, anyway, so thank you very much. I'm not making fun of Denmark. I love Danish people. I love Denmark.
You're welcome.
I do struggle over there a little bit. And the few words I learn, I say it to people in Danish and they just respond in English anyway. They know that I'm not a Danish speaker. All right. So we're going to be talking about muscle glycogen. Yeah. And why is it important? Okay. Now, what I do like to do though sometimes is to start off saying, how did you actually get to where you are now? In terms of, were you a sports person who then got interested in research and did exercise research, or were you a researcher who realized how important exercise is and then started doing that? How did you get to where you're at now, roughly?
I mean, the easy answer would be both, actually. So I don't know what I'm a researcher. As long as I remember, I've always been interested in biology in general, always also as a kid, and but also hearing also sports science and limiting performance and whatever. Impressed by sports in general, and even though I'm not a big talent, I've done a lot of sport myself. So it's pretty much.
Did you say you're not a big talent? Is that what you said?
Yeah, I'm in sport or whatever. Yeah. I've done a lot of sport myself, just but never on the really high.
But it wasn't like, I'm really into sport and there's a sports science course. It wasn't like that. It was more. It didn't work.
Just interested in So in general, so you say your question was actually how I got into it. I wouldn't rather say I never got out of it, whatever. So you can say so. I've been into it all the time, actually.
That's true. Okay. So, all right. So you're from Southern Denmark?
I'm actually from the northern part of Denmark. I actually been living in Aarhus, Denmark, you can say, but I actually say I'm from the northern part of Denmark, but it's not far. It's like moving around in Melbourne, you can say, in Danish terms.
Yes. Yeah. So, but you did your undergrad, your PhD, your postdocs, and all that.
I did my undergrad in Odense. So there was sports science, and then I moved into biochemistry, biology, as my master. Actually did my master thesis here also in free radicals. It was actually at that time, it was actually hot topic. So I did actually and set up a lot of methods, and that I actually realized there that I was really enjoyed being in the laboratory and set up methods, and also realized the importance of being able to measure something precise, validity, reliability, and so on. So
Yes.
that was actually my take on it. And then I was lucky to get a PhD at that time, also in Odense, partly at the University Hospital. And I actually spent some of my time in Melbourne at that time also to learn some methods on whatever muscle contraction and muscle fatigue and so on, and effects.
Oh, was that with Michael McKenna or?
Yeah, I had a research stay there. Yeah,
Nice.
Learn the method I'm actually still using here in Odense.
Cool. I thought we decided it was UNSA. I learned that. It took me a long time to get that right. But yeah, Odense. Yeah. Okay.
Odense. I'll do it in English.
The Australian guy calling it UNSA, and you can call it Odense if you like. All right. Yeah. So if we think about, you were saying before we came on that it'd be nice to talk about the history behind, glycogen and whether it's important during exercise, etc. Did you want to give a little spiel about that?
Yeah, the title of the talk here is actually why muscle glycogen is important. Actually, so you already answered the question. It is important, you can say. Okay. But actually, it was actually found glycogen in the mid 1800s, 1850s, 60s, or whatever. And that could measure at that time glycogen, and you can also measure lactate at that time. So, and they could actually also measure that lactate was higher in active muscle than in non-active muscle. They could actually do that in hunted deers and so on. Then they measured that, and also birds and so on. And they could actually even also isolate. That was also, at that time they used, and in the beginning of 1900s, they often used the toed muscle and so on because they're easy to work with, isolated muscles. So they could even measure in an isolated muscle when if they stimulate them to contraction, the lactate levels are higher, and also Weiss could actually show in the 1870s that glycogen actually did decrease, or indications on that. So there's a lot of indications that the carbohydrate was used during exercise, and that actually led to the emerging idea that or belief that actually the energy entirely comes from carbohydrate. And there was a long discussion, could you also use fat and so on. So it wasn't actually until the mid 1900s, 20s, 30s that they actually couldn't. It was actually shown that you could actually also use fatty acids for contractions. So it's actually been so it's already known, as I said, from more than 150 years that glycogen or carbohydrate is quite important actually. And they could also at that time measure respiratory exchange ratios. So that means oxygen uptake and CO2 production. And that says something about if you are using carbohydrate or fat actually. And they also, they often use, they could see during exercise, RAR values were always high, showing that you're only using carbohydrate. So that was one of the proofs at that time actually.
And can I say, at that time, were they assuming that all the carbohydrate was glycogen, or were they also thinking about glucose?
Well, they didn't really know the source, but obviously when they did measures at the muscle level, isolated muscles, it had to be something in the muscle. So they often didn't use glucose in the solutions and so on. So it must be something in the muscle, which would be glycogen then.
Right, and I guess they didn't think, because the RER, that wouldn't have been in the isolated.
Yeah, that would be. Yeah, no. That will be on the whole body exercise. They actually did that on horses and so on. That's quite amazing. Yeah. Yeah,
I'm just wondering if they were thinking it was just all glycogen, or did they start thinking, oh, it might be a bit of glucose as well?
No, but they couldn't distinguish it because they didn't. They could just say carbohydrate, right? So that was the only thing. Yeah.
So I guess it wasn't until later when they had traces and things. Yeah. So that's and the AV balance.
Yeah, but you could also in the one of the really maybe the biggest exercise physiologists was AV Hill that was actually in the beginning of the 1900s. They could actually start measuring glycogen and lactate, and they actually found also creatine phosphate and so on. But they could actually see that your lactate, there was pretty much lactate they measured, that you could also say that lactate was produced during stimulation, and also led to when they blocked the production of lactate, the glycolysis, they could also show that the toad muscle couldn't actually contract anymore. And with the same information also, they could see, well, the harder they stimulated the muscle, the more lactate was actually produced. So that actually led to the logical idea that the lactate hypothesis of contraction, meaning that actually at that time thought that lactate was the signal to the muscle to contract actually. So and A.V. Hill actually got the Nobel Prize in I think it was 1922 for that.
So we should retract that.
Partly.
We should retract that Nobel Prize, I think. So he's thinking that you're contracting. Obviously. Okay. Well, this is a perfect time to say that science is incremental, and that was genius back then. But then we realized, and one thing is, I had Stu Phillips on here. He's big on protein and muscle adaptations and things, and he was more than happy to say that some of his initial work, what he thought, he now realizes is not really correct. So he was thinking you needed to have, you needed to eat meat. Now he realizes you can get enough protein from animal and whatever. So the point is, science evolves, and of course. So he was thinking the glycogen was broken down to lactate, and then lactate was then stimulating the contraction. That's interesting.
And that's that's the general. We actually have the same thinking often. Actually, just the two things correlate or are associated. We often see a link between the two, right? So we still do that actually. So it's obvious to do that. But at that time, they also used, RER values quite a lot. Actually, Krogh and August Krogh is one of the, also one of the big physiologists, and Lindhardt. They could actually measure in 1920s that also if you are, they were actually manipulating with the diet. So saying if you're on a high fat diet or high carbohydrate rich diet, they could actually see different RER values as you would expect. So that meant actually, you could also see that you were less efficient producing ATP or energy. You used more oxygen per given work you're doing when you're on a fat diet. And it was also harder actually. So that was actually one of the first mentions actually where the story starts for me. Saying they could actually, they also noticed when you're on a high fat diet, that means low muscle glycogen levels, they actually was a lot harder to work, and they had to stop before expected and so on. So that's the first notice. So they actually just noticed in that time, well, carbohydrates apparently important for exercise capacity. So,
but now it's debatable on Twitter though. People don't necessarily agree with that.
No, but that's another thing. But you can come back to that actually. But it's
exactly. We'll get back to that.
But they didn't really. But now we're talking about, as your question alluded to before. Actually, there was just carbohydrate in general. We couldn't distinguish what it was actually. Was it from the liver, blood, or intestine, or is it muscle glycogen we're talking about? So it wasn't actually until there was a big step until early 60s, late 60s.
Bergstrom and Holtman.
Bergstrom, right. The biopsy technique we actually started to use, right? So it's actually called the biopsy needle technique, which actually was used before, but we use it quite a lot on the muscle sampling. And that actually some of the first studies I did was actually doing exercise, and they could actually see that and taking biopsies before and after, even on themselves actually. Some iconic studies I did actually. So they did actually
9 biopsies.
And I took biopsies. Right. So they exercised until exhaustion. So they could actually see at that time, well, whatever you did of kind of exercise, different intensities and so on, you had to stop exercise, or exhaustion was actually correlated with very low glycogen levels in the muscles.
Well, that's
and they could
interesting.
also that was actually first, and they could also see, well, now they also manipulated with the glycogen, so they could actually have different diets. So they had the same subjects reporting 3 times to the laboratory, and depending on the diet, they had either a mixed diet, then they had a medium glycogen levels in the muscle, or they could have a high carbohydrate diet for 3 days, and they had really high glycogen levels, or the opposite, high fat diet, low carbohydrate intake for 3 days, and they had very low glycogen levels. They could actually see, well, both the utilization of glycogen was higher when you had higher glycogen levels, and they could actually exercise for 3 times as long actually as with a high-fat diet, and they actually were exhausted at more or less the same low levels of glycogen. So that's really, and that's been shown, I mean, numerous times, I can say, actually.
So so we're talking about Bergstrom and Holtman in the 60s, but also Christian. So another one's from Scandinavia, Christensen and Hansen in like 1939, etc. You know, like you think, oh, I'm doing this really hot work, you know, giving, you know, manipulating diet and giving carbohydrate drinks, and you realize they did this stuff in 1939 as well.
Yeah, they could actually show that word at exhaustion. That was actually, I mean, prolongation of the Crow-Linhart studies I told you before. So, well, at exhaustion, they could actually give the subjects fairly high 200 grams of carbohydrate, glucose they actually gave in. And then it could actually, whatever, extend exercise again. So that was pretty iconic also, right? Yeah.
Wow. Yeah. That's a really nice, it's really nice to think through that and to recognize, because, you know, more and more it's, you know, it's hard to keep people's attention span sometimes. So, you know, even Bengt Saltin, you know, people start to, so he died 2019, I think. And you sort of think, oh, I hope people don't, you know, just quote the papers 2 years ago or whatever, you know, they realize all that work from back in the 60s, et cetera, that he did. Golnick and, you know, all these legends.
But you're right. I'm actually, we're getting old now, Glenn. So we're getting interested in history also. So if you read some of the old paper, I mean, there was really a golden age in the 20s, 30s, and that's actually where you really started exercise physiology and the importance of exercise and so on. So we got so much knowledge. I mean, they're really pretty good at measuring things at that time. And
it's amazing.
If you read papers, some of the questions they ask, we actually have the same questions now.
Yes.
So that's quite amazing. So
you know, they'd collect, you know, when you said RER, they'd have to collect the air in a bag, and then they'd have to bubble it for, I don't know exactly how they did it, but they'd bubble it. It'd take like 2 hours or something for each air sample. To measure it. And now because I'd always say to my students, so when as you know, these automatic analyzers would come along, I'd still say, look, the best way to measure it, and I'm most confident, is with Douglas bags. So I'd make my students do Douglas bags, and they got this nice fancy analyzer sitting there. And it's like, oh, but it takes 2 minutes to do every sample. I'm like, yeah, we used to take 2 hours or something, you know.
2 hours. That's
I'm just an old dinosaur, I guess.
But the good thing about it is maybe that you have to think a little bit before you do experiments then, because if it's easy, you don't have to think a lot. You just do the experiments. But here you actually have to think workload per whatever.
Exactly. And also you got to think, you think, is this VO2, is this RER, is this what you'd expect at this particular workload during a max test, for example, rather than just start the test, do the whole thing, and then you realize the mouthpiece is back to front or something. So
but I think it's actually with the Bergstrom needle. I mean, when you talked about starting taking biopsies in exercise physiology in the mid 60s and so on. So I mean, it's fairly easy to do actually if you're allowed to it, and then. So, I mean, we know so much about muscle actually compared to other tissues, you can say, and that is because it's easy to take biopsies, at least from the vastus muscle. So, I mean, if you think about it, liver, or kidney, whatever, you can't really take kidney, you don't really know as much actually.
The other thing I've
actually been lucky to work with Bengt Saltin, as you mentioned. That's actually been one of my big inspirations and mentors, and been very lucky to work with him in his last days. And at one of the experiments, we've done a lot of cross-country skiers and so on. And in the weekend we took, I actually think he took 88 biopsies in one weekend.
Wow.
In the skier's arm and legs. But the point is actually that during a coffee break, I just asked him, Bengt, how many biopsies have you ever taken in your lifetime? He said, I've been trying to calculate. I took actually 30,000 in my lifetime, he said, so far. Actually.
Wow.
And I thought it can't be, but actually, if you think about it, it actually is true, actually. And if you count, I mean, conservatively, you take out 100 milligrams, sometimes 200 milligrams or whatever. So 30,000 biopsies, that's actually 3 kilos of human flesh, actually. There's a lot of information in that, you can say. And he's not the only one taking biopsies, so.
Absolutely.
So we know a lot about muscle, and it's easy to get knowledge about it, muscle cells and so on, in humans at least, right?
Yeah, and the other big step in terms of working out how much is glycogen, how much is glucose, is, you know, traces, and then again, Bergstrom and Holtman and other people around there that were doing AV balance and looking at the difference across the leg Yeah. So
Yep.
classic
Yeah.
stuff. Classic.
Yeah.
Okay.
Yeah.
All right. So,
Yeah.
so should we give a bit of a background? Most people would have a bit of an idea of this, and you've
Yeah.
already said, anyway, let's just give a bit of a background, the effect of intensity and duration on muscle glycogen use. Yeah.
Yeah, but and as I said, we've known that for a long time. But the higher intensity, the more carbohydrate you use, actually. So it's a general, it's actually exponential, you can say. So after whatever, above 70-80% of VO2 max, you're actually nearly using entirely carbohydrate.
Mm-hmm.
And it's also very much dependent on of course, duration. Actually, in the beginning of exercise, you're actually using, superior or more glycogen than you would actually do during end of exercise, even though you're exercising at the same intensity. You're using in the beginning of the first 10-20 minutes of a given exercise, you're actually using high amounts of glycogen, and that's probably because you have to start uptaking the glucose uptake and metabolism and so on. So that's glycogen is the readily available substrate. So it's intensity dependent, very, very much actually, and it's also duration dependent to a lesser degree. And but it's also diet dependent. So it also pretty much depending, as we said before, that's been known for a long time, that if you actually have a high carbohydrate diet, even if you're exercising at low intensities, you actually have a high combustion of carbohydrate and muscle glycogen, you can say.
Oh, sorry. Sorry, you're saying if you've had a diet where you've had a high carbohydrate, you get a high level of glycogen. You're saying that you will use glycogen at a lower intensity than you would normally.
Yep. Yeah. Right.
Okay.
Definitely. Yeah. So it's pretty much diet dependent also. Yeah.
All right, but it would still be low. I mean, I just don't want people to think that if they're going for a walk or something, they're using a whole bunch of glycogen. They wouldn't be using much.
No, it's pretty much. No. I mean, it's actually, as I said, it's only actually you're using it when you get above 60-70% of VO2 max. It's actually increasing exponentially. So
yeah, and the classic sort of Rominj study was sort of in trained people, 65% VO2 max was like 50-50 carbohydrate and fat. But then, but then, as you said, as it gets harder, there's an exponential increase where glycogen becomes much more used compared to glucose. So glucose sort of goes up slowly with intensity, but glycogen sort of goes up and then just goes nuts.
Right. But again, the point is actually many studies has actually been done on first of all on the cycle ergometer, but also on a fasted state. So my point is also that it's pretty much I mean, it's well known, but it's not really knowledge when you talk to students about this. It's actually also diet dependent. So if you have been using a high carbohydrate rich diet, you can actually exercise at very low intensities, but still actually have a high carbohydrate utilization.
Okay, so this is point that you touched on, that when you have higher glycogen, you actually use more. Yeah, so that's a classic thing, and that's during my PhD we found that where we had like moderate, high, and then we'd done different used different diets to end up with the same glycogen, etc. And we found a really nice relationship between. So when you start with high glycogen, you use more than when you start with low glycogen. Now the thing that I could never quite understand was the fact that, as you said, at the same intensity. So they were doing like 65% of VO2 max, and they were actually untrained. So we just did 40 minutes, and they were able to do it with the low glycogen. I was low to moderate. They were able to do it. Now, when they had the high glycogen, they used a whole bunch, and they were still able to do it. And I was thinking that's not very smart of the body, because glycogen is so precious, compared to fat that can last, forever. Why are they using, do you know what I mean? I know that the enzymes will be.
Yeah, but there's no idea in it. You can say, or at least we don't understand the idea when they say it's because it's going to be a limiting factor at some stage. So why don't you save it actually? So
yeah, exactly.
But that's actually again, But again, you can say, well, with training, one of the key things with training is also that you get high. I mean, twice as much glycogen at rest compared to untrained. Part of it would actually be what we call supercompensation, but at least actually when we take resting biopsies, they have more than twice as much as untrained. And they also are able to use more fat actually, but still actually in the train they use more glycogen when they have high levels of glycogen, and there's no really idea in that.
It's really weird, isn't it?
Glycogen is more efficient to use glycogen. I mean, that's also, it's 10 whatever, about 10-15%, maybe more 10% more efficient to use carbohydrate than use fatty acids. That means you use less oxygen per given work you're doing.
Yes, so that's a very important one. Yeah. So, so just to state that again, that you actually using less oxygen per unit of energy when you're using carbohydrate versus fat. So that's maybe another one we'll get to later if we talk about sort of keto diets and things. So yeah, and also you can't get the energy as quickly. So it's definitely the first choice is to use carbohydrate. Yes. All right.
But again, you can say, well, there's more philosophic question. I mean, as you say, why use all that glycogen in the beginning? Actually, because you just because you got lots of it. But again, the muscle wouldn't actually ever know that you're going to exercise for 20 minutes or 20 hours or whatever. So you can't really.
Yeah, that really did my head in. I still don't get it. So that was 1991 to 1995 was my PhD. And that was one of the things in the conclusions and discussion was like, why does the body choose? And, I've brought this up before in the podcast and they say, oh, it's because this enzyme is more activated and whatever. Yeah, I understand that, but it just doesn't seem like a particularly smart thing to do.
No.
All right.
But depending from what point of view, we're just talking endurance now. So, I mean, there might be other important things actually than just endurance, right?
No, there's nothing more important than endurance. Well, maybe that's a good point as well. So maybe it's worth mentioning to people that when you're doing high intensity exercise, where you can only really get the energy from creatine phosphate, which we won't really go into, and glycogen to get the energy fast enough. Part of the reason the body uses the glycogen is because it's already sitting there compared to the glucose, but you also get more ATP from each glycogen molecule than each glucose, right? So So
and you can also say, I mean, it's also one thing is actually the efficiency, but also if you compare carbohydrate in general or glycogen compared to fat combustion, so you can also convert ATP faster. ATP, that's the final energy you're using for contractions or exercise, and you can actually do it fast, actually twice as fast. Actually, you can measure that biochemically. You can convert carbohydrate to ATP than converting fat to ATP. So that's probably also the reason that when you're exercising at high intensity, you can't actually combust fat actually.
Exactly.
So that's one of the explanations for the term go bonk actually when you're doing whatever. The classical is actually when you are bonked. You're right. Yes, when you have been exercising for 2-3 hours and you can't exercise. I mean, you in a marathon and you have the feeling that you can't really run really fast. You have to walk now. That's actually because you are actually low in muscle glycogen. That's one of the reasons you have to. And then you actually can only use ATP at a lower rate, and then you have to slow down the utilization of ATP or exercise intensity or whatever.
Right. So that reminds me of one that I've another one I've always thought about, which is the classic Coyle study from 1986, where he did carbohydrate ingestion or placebo, artificially sweetened, and then these trained people exercise at 70% VO2 max for as long as they could. And they went 3 hours on placebo, and they went 4 hours when they drank the carbohydrate, and they didn't know, right? And the thing is, they the glycogen use. Now, this is where we need to start getting nitty gritty. When you just do the biopsies and measure glycogen in the mixed muscle, it looked like they didn't really use any glycogen for that extra hour, and it was really just they were using the carbohydrate they were ingesting, and that was maintaining their carbohydrate oxidation. And they went longer. Now that's something. So with Jorgen, I had Jorgen Jansen on here, as you know, and we talked about that. It's a bit, it's a bit controversial, a bit of an argument of, are you actually using glycogen during that last hour? How do you know you're not using it in different compartments and things like that? So what do you think about that? And also different fiber types. So you might be using it in your,
But I mean, yes. So starting now, it's actually glycogen is just not glycogen. We can actually get into more into that. That's actually what we've been working with quite a lot.
Yes.
But in general, if you take a biopsy and take a average glycogen levels in the muscle, I mean, most studies have shown no sparing of glycogen when you actually ingest carbohydrate during exercise, even though, and that's actually one of the, you can say, I don't know if it's controversial, but one of the arguments saying, well, is glycogen that important actually? But we still actually, there's many studies showing, and actually all studies have shown that glycogen is important for muscle function or in performance and so on. And we also know that ingesting carbohydrate during exercise, at least prolonged exercise, that means more than 1.5 to 2 hours, or if you do high intensity intermittent exercise, it would actually improve your performance. But it's not the reason that you improve your performance by ingesting carbohydrate during exercise. It's apparently not because you are saving any muscle glycogen, at least on average level. So that could actually be on the different fibers or localizations of the fiber and so on. We don't really know. That's one of the coming research we're going to do now, actually.
Yeah, so I guess there's a couple of things there. So one thing is, the classic coil study showed the glycogen use during the exercise was unaffected by the carbohydrate ingestion. And as you said, there could be, there's a bit of a debate, like, well, what about in slow fibers? And what about if you look at different, within the fiber itself or whatever, but it looks like it's not really affected. But then the other thing I sort of touched on was that for the extra hour they went, it looked like they didn't really use any glycogen. They were just using the glucose, and that enabled them to keep going. But again, what do you think, about this sort of compartmentalization, and what if there's less glycogen, around the sarcoplasmic reticulum or, whatever? That's the sort of work you've been looking at,
Yeah, we've been quite interested in that actually in the given fiber. It's actually glycogen glycogen is actually the storage of glucose. So actually put a lot of glucose molecules together, and then you have what we call granule on a molecule, or sometimes you also call it particle maybe. So that's just a lot of glucose put together in these particles. And they're actually located. We can actually, we often do, I and colleague Joachim Nielsen has actually been doing a lot of that actually, and try to extend some of the early works by Fridén and so on in the 80s. So we're using this electron microscopy pictures, which means you can actually enlarge the fiber, and you can actually have a look. You can actually see the glycogen molecules and a lot of other things. And then you can actually see where it's located, glycogen in different compartments of the muscle. So you can say a muscle fiber is actually in general very crowded. So a muscle fiber is just a given cell, and most of it would actually be the contractional apparatus, which we call the myofibrils. That's whatever. In general, it's around 80% of the muscle fiber will actually be filled up with these contractional elements. And then you have mitochondria and so on, and sarcoplasmic reticulum. We can come back to that actually. And then you have the glycogen and fatty acids and so on in muscle fiber. So glycogen is actually located in 3 different compartments, we say. Some is actually just below the membrane of the muscle fiber, and it's a very small part of it. 5-10% of the glycogen is actually located there. And then most of it would be located around this contractional apparatus, the myofibrils. That will be 80, maybe up to 90% or whatever, around the myofibrils. And then some of it would be located inside the contractional apparatus. That's some would know it's myosin and actin and so on. It's actually located between the actin filaments. And that's what we call intramyofibrillar glycogen. So it's actually 3 compartments: subsarcolemmal, and between the myofibrils, and inside the myofibrils. So we try to estimate how much you're using in the different compartments, and Most, but not, but if not all studies has actually shown that during different kinds of exercise, you're actually using relatively more glycogen in this compartment inside the myofibrils, what we call the intramyofibrillary glycogen. Even though it's only 10%, it's actually using relatively more. And it's also the compartment correlating best with the impaired muscle function, and you have and also different measures of muscle fatigue and so on. So we believe that's actually an important localization of this this glycogen. So we're trying, but we don't really. We would like to manipulate with the different pools actually, but we don't really know how to do that actually so far. So we can't really distinguish. You can just observe how much you're using and so on. But the interesting part is actually saying, well, this is actually we believe in most studies that it's correlates with the markers of fatigue and endurance and so on. That I mean, we also do a lot of studies, exercise or carbohydrate studies has been done on rodents, mice, and rats and so on. And we're pretty similar to rodents, but in terms of glycogen, we're quite different actually. So humans actually have a lot more glycogen, and that's in the order of 4 or 5 times more glycogen than rats and mice in the muscle. So they apparently rely more on liver glycogen and blood glucose uptake and so on.
They tend to rely more on extracellular, so yeah, from the blood with fat and glucose. So
they have, you can say, and you can say they have, or we can actually observe they got 4 or 5 times less glycogen in the muscle, but still actually they have equal amounts of this pool of intramyofibrillary glycogen as the humans have. So they choose to have this, I mean, all the glycogen, nearly all the glycogen in the intramyofibrillary glycogen pools, as we believe is important actually. So that's actually kind of where you can use comparative physiology. We would like to do it in other animals.
And sorry, did you say that's not a very big pool in humans?
No, it's 10 up to 15% or something like that. Yeah.
Okay. And you feel like that's the one that correlates best with fatigue?
Yeah, definitely. Yeah. And also, I mean, one that maybe we can go into why glycogen is important. That's actually what we've been trying to elucidate the last 20 years, I think. So you can say, well, glycogen is actually, we can correlate when you contract muscle is actually a series of signals. First, the nerve stimulation of the muscle fiber, and then you actually have to this is actually electric signal, what we call the muscle excitability. And that's converted into a signal in the muscle, which is calcium. So calcium is released from sarcoplasmic reticulum, and that's actually the signal to the contractile apparatus to contract, and you get the muscle shortening. And then at the same time, you have to pump this calcium back to sarcoplasmic reticulum. So calcium actually cycles in and out of the sarcoplasmic reticulum. And we can measure both directly, we can measure some of this calcium release. We can actually measure with low glycogen levels, you actually have an impaired calcium release. I mean, you can also see with low glycogen levels, in this particular, with this intramyofibrillary pool we look at now, it's actually you have a decreased release correlates with that, and also with the levels of calcium, you can measure that. We have done studies with colleagues in Stockholm on single fibers also. So apparently, it's actually affects the calcium release rate. That's the signal to muscle contraction. So, and when I say low levels, it's actually, I mean, normally if you're untrained, you have glycogen levels in concentrations what we call 400 millimolar per kilo dry weight. So if you're below whatever, often we say in general 200 and 250 millimolar or whatever, but then you can actually see effects on the calcium.
I guess that's the other thing, that it doesn't really get that low. So you know how you were talking about the classic Bergstrom and Holtman and I think Saltin, you know, but they did the 30% VO to max, the 65%, and then the 90%, and it was only really the 65% to exhaustion where it got really low. So you know, it's the 30% obviously they never reached fatigue. The 90% they probably fatigued for other reasons, but it doesn't always get that low. That's the other thing with the Eddie Coyle, right? That it was only sort of down by, I don't know, 75% or something. It doesn't tend to get down to nothing. But again, do you think it depends on the pools And maybe the fiber
first of all, you
types-
have to bear in mind that the way that this kind of most glycogen studies has actually been done on steady state exercise at 70-75% of VO2 max until exhaustion. And that means you only are mainly activating type 1 fibers and not so much type 2 fibers. And when you take a biopsy, you actually get, at least in the West, was 50-50%. So what we're talking about now is actually average glycogen levels.
Yes.
So the reason you're not lower could be that you actually, or it actually is part of it, that it's only type 1 fibers which are lower actually, and you still got lots of glycogen in type 2 fibers, at least some fibers. So there definitely heterogeneity in it. And if you want to go really low, often we do exercise when you have to do, we and colleagues in the field, you have to do sprint hit training in between this steady state exercise. Then you can actually get a lot lower. But still, you're right. It's seldom we go below 100 millimolar or whatever. We can measure that at least, or so we never really go bump, you can say, or really go empty of glycogen. You have stop mechanisms doing that.
So is it possible that just a certain, maybe 3/4 of the fibers or something might be sort of close to depletion and 1/4 are okay? So when you biopsy, it looks okay, but there's not enough fibers to do the work. Do you think? Is it?
Yeah, I think so. That's actually what I believe. That and it's also a bit funny. You can say, why would you do that? Why wouldn't you actually use all your fibers? But apparently, you're only activating most of the type 1 fibers, and then later on type 2 fibers. At least if you do steady state exercise at relatively low intensities. But still, also when we measure fibers, at least when you do high intensity exercise, there's quite a big heterogeneity, not only between type 1 and type 2 fibers, but also within a given fiber type.
Yes.
We did recently, as I said, most studies has actually been done on a steady state exercise. We like to do that in the laboratory because we know how much exercise people have done exactly and so on a ergometer bike. But we try to do some real life, we've been involved in soccer and also strength training. It's actually believed that in strength training, you don't really need glycogen, or you need glycogen, but it's not a limiting factor. And that's because if you take biopsies before and after whatever given training session, 1.5 hour of strength training, you're only below to at most 50% or something like that of glycogen. So it will never be a limiting factor. But when taking biopsies, we recently did a study on some of the best Danish weightlifters and power lifters and so on. Pretty impressive people actually. But before and after a normal training session with squat and deadlift and so on, they actually also were just down with 39% of the total average glycogen. But we could actually see, that was together with Joachim Nielsen, actually my very good colleague in this field, that some of the type 2 fibers was completely empty actually. That means no glycogen in them whatsoever.
Wow.
So that's just demonstrating that, well, it may not on the average level, muscle level, be important when you actually lose some type 2 fibers. So that could be part of the explanation. Why it's like that, we don't really know actually.
That's interesting. You know how you said during prolonged exercise, you mainly submaximal, you're mainly using slow fibers, and then as you get depleted, you start to recruit more and more fast, but it's still mainly slow. It's interesting. I always thought during weight, so I must be wrong here. I always thought during weight training, you'd be using all your fibers, or are you? But it's just the fast fibers are actually producing the high forces, and they're the ones that are getting depleted.
Yeah. But in general, you're using all your motor units, all your fibers. That's actually what they're good at, this strength train.
Yeah,
recruitment. But still, we could actually see, but that's pretty much power they're doing. So I don't know. Apparently, we can just see energy utilization by glycogen, you can say, or glycogen utilization. They actually have used more in type 2 fibers, and some are really, empty, completely empty, right?
I guess that makes sense, because the slow fibers are better at using using glycogen aerobically, I guess. They've mitochondria. Okay.
So that's part of the heterogeneity. And we also done, as I said, I've been associated with the Swedish Winter Sports Research Center, together with Hans Christer Holmberg, who's actually in lead of that. or was actually. So we done some sprint skiing also. That means 3.5 minute all out exercise. And there's competition within cross-country skiing where you do that 4 times in a day with rest periods would only be down to 20 minutes before the semi-final and final and so on. And you can say 3.5 minute all out, how much glycogen do you really use? But we actually found that taking biopsies before and after the 3.5 minute all out, they actually decreased by more than 20% actually of your total glycogen pool. That's quite a lot actually on 3.5 minutes. So that's also highlighting that high intensity exercise is actually purely relying on muscle glycogen.
You'd know the classic Hermansen paper from where they did a 30-second sprint and they used 50%. And we actually also did a study. We're looking at AMPK activation, and we did a 30-second, the Wingate. So just so people know, this is not 30-second sprint where you you pace yourself. This is as hard as you can go from the very first spin, and then you go as hard as you can and you drop off and all that. 50% in 30 seconds, which is pretty amazing, right? Now when you compare that to like is that the 70% VO2 max, it would take you about an hour to use 50% or even more.
At least.
But that's really interesting. Now I do have a question here. I just wanted to, when we talked about calcium release, Calum Brownstein said, are we any further to understanding how glycogen depletion reduces calcium release? So you said it does, but do we know why? How? So essentially, especially as calcium release doesn't require ATP, is it due to reduced calcium reuptake? So that's another interesting thing. So just to sort of summarize a bit. So how you're saying that calcium is released from the sarcoplasmic reticulum, and that's important for the contraction. And when your muscle glycogen depleted, you said there's evidence that you have less calcium release, but you've also got the calcium uptake. So he's asking about that. So maybe if you can just explain that a little bit.
It's a really good question actually, and I have the same question actually. We don't know. That's where we're going, but it's But he's completely right that this muscle activating mechanism of releasing calcium, activating the contractional apparatus, doesn't actually per se use ATP. We're using quite a lot of ATP to pump back calcium in the sarcoplasmic reticulum. So you can say, why is that important? But we know there are quite a few regulating mechanisms on the calcium release channel. One of them would be ATP. And there are also different kinds of phosphorylation and so on. So what we believe is actually that the local ATP levels, it's actually really narrow space you have in the muscle where you release calcium would actually be ATP dependent. So the idea, or what we know, is actually that the ATP, a cell is just not a soup where everything floats around actually. So it's actually located, and the interesting, as I said, the intermyofibrillar glycogen, which we believe is the important one of the glycogens, is actually located on or near the sarcoplasmic reticulum where you release calcium. And you also have a lot of the enzymes, the glycolytic enzymes, converting glycogen to whatever the first steps in the metabolism to lactate also is actually located also on the sarcoplasmic reticulum membrane. So the emerging idea is actually that you produce ATP where it's used actually. So you don't just produce it in a mitochondria or whatever, and then they float around and eventually diffuse to where it's used. You actually produce it where it's needed. And you need a certain ATP level to be able to open the calcium release channels. So that's the explanation actually. And we know that also because I was lucky to be postdoc in Melbourne actually, in the La Trobe University, together with George Stevenson and Graham Lamb actually. And they actually have this very unique model, which I actually set up also here in Odense. On the mechanical skin fiber. So that was actually more or less developed by George Stevenson. So you can actually, that's a fiber where you can actually skin off the membrane of the muscle fiber. And then you would think everything is actually floating out of the fiber, but it doesn't actually. So you actually still have all the enzymes, still got glycogen, still got whatever, nearly all things. You have such few buffers which actually diffuses out. But you can actually take this fiber and mount it and stimulate it electrically, just like an intact muscle fiber or intact muscle, and get contractions. And why do you want to do that? That's actually quite unique because you can actually have an intact signaling mechanisms in the muscle fibers. You can still actually do this electrical signal and release of calcium and contraction and so on. In this fiber, we can keep ATP constant. So we can manipulate with glycogen levels, have them high or low,
Okay.
keep a pH constant or whatever, keep everything constant as we like to do in research, and only manipulate with glycogen. And then we can actually see in these ones that glycogen is still important, even though you've got plenty of ATP floating around, but it has to be produced nearby the release channels. That's the least. Yeah. So that's, now what about, that's probably why we do it. Yeah.
You know, so isn't getting near fatigue, isn't calcium reuptake also reduced? So I guess I wanted to just make sure it was clear. So he was saying the calcium release is reduced when muscle glycogen is low, but is it partly, and I know you said what you said, but is it partly if you're not taking it up as much, then you don't have as much calcium to release, or is that not right?
It's a good question. Right? Yeah, but because you, I mean, the uptake is important also, and it's estimated that we use. I mean, part of, you always think that intuitively you think that you used all the ATP by the contractile apparatus, but you actually it can be estimated that depending on exercise type and so on, it's only about 60-70% maybe of the energy used by the contractile apparatus. The rest of the ATP or energy is used to mainly pump calcium back to the SR, so you are able to release it again on the next stimulation. And part of it is also used, a smaller part of it is also used by the sodium potassium pumps in the membrane, so you can keep your membrane potential and excitability. So it would actually be more, I mean, directly thinking, well, it might actually be the uptake of the calcium, and we're actually doing experiments on that now. And you can say initially we can see some effect, but not huge effects actually on glycogen on the uptake. But it could actually be, I mean, if the uptake was down, you would have less calcium to release, and that could actually explain maybe the release rate. But with, again, going back to the skin fibers as we had, we can actually force the calcium release channels to open in different ways. You can add caffeine and so on. And you can actually see the sarcoplasmic reticulum still got calcium inside. So it's not really limiting. It's actually more the opening of the channel. And also
that's interesting. So, okay, if we're talking about fatigue, I guess we need to give people a bit of an overview that you know, it could be coming from the central, like the brain sending less messages. It could be coming from the spine, sending out less messages to the muscle. But then, you know, once you get the message arriving at the muscle, you've got the excitation-contraction coupling. Do you want to just say what that is and whether muscle glycogen can affect that?
Yeah, but that's the very first step, and we got this term excitation-contraction coupling, and that's actually that you excite the muscle. That's actually mean that you depolarize the membrane. So if you have a given membrane potential, you actually depolarize it, and then actually that's actually a signal to open these calcium release channels in the sarcoplasmic reticulum, and you get the release of calcium. And we already talked about glycogen role in calcium release, as we believe is important. But there's also been lots of experiments on the importance of excitability, or at least the sodium potassium pump, which actually in turn is important for our excitability, so keep the membrane potential. And they use very little energy, 5-10% of the total energy, maybe more 5 than 10. But still important actually. And they are actually, I mean, it's well known actually that they're actually fueled by glycolytic derived ATP. So that's before you go into, that's actually anaerobic before you go into the mitochondria. And that's probably an evolutionarily conserved way, because we actually had sodium potassium pumps before we had the mitochondria. So they actually, so it's important for all cells. And glycogen is actually, we have to mention that the glycogen is actually a very universally used substrate, from the very basic bacteria to complex organisms as human is. So all cells actually using glycogen, or mainly nearly all cells. So the point is actually that so glycogen or glycolytic derived ATP is actually fueling the sodium potassium pumps. So that's more the anaerobic part of it. So that's a lot of, and that's actually not only muscle cells, it's been demonstrated in nearly all cells measured in. And
that's in slow and fast fibers, or?
Yeah,
must be, I
both
guess.
in apparently, yeah. But we did mainly with the skin fiber used. Maybe we did recently also data on that showing that the sodium potassium pump is actually slowed when you have low glycogen levels, or if you block the glycolysis and so on. And that's also been shown if you speed up the glycolysis, you can also have a faster priming of the muscle fiber. That's been shown by Graham Lamb and colleagues. Yeah.
Yeah, and it is amazing that because I was working at Victoria University with Michael McKenna, and he would always be pointing out that the potassium levels in the blood would go from like 4 or something at rest up to you get up to 8. So it was indicating that the muscle was not able to maintain its action potentials that well, that it was losing potassium. Yeah. And that could play a role in fatigue, you're saying?
That could play, but that's debatable, you can say. That's one of the fatigue mechanisms to say, why do fatigue? And when we talk here fatigue during high intensity exercise, that's only during really high intensity exercise where you do a lot of stimulations, a lot of action potentials, and then you actually eventually lose some potassium from the muscle. We can measure that in the blood, actually, as you say, up to 8, 10, even more sometimes. And theoretically, if you add that amount of potassium to a muscle in vitro, you actually would have a depolarization of the muscle and actually lose your excitability and contractile ability. But still, actually, also you can say, well, you have lots of you actually stimulate the sodium potassium pump also, and excitability is pretty complex. Actually, you've got different channels you can open and close and so on. And definitely, we know that from studies by Thomas Peterson in Aarhus and so on, that the chloride channels can be closed and you can increase your excitability. So all in all, when you put these protective mechanisms together, maybe it's difficult to believe that loss of excitability would actually be the cause of fatigue even during high intensity exercise. Yes. But then we can move the argument. I've been working with this and been interested in that also. I mean, you can say, where do we measure potassium? So there's not only, where potassium is important is not in the blood, it's actually around the muscle fiber or inside them. We have this T-tubular system. It could actually be pretty high in the T-tubular system. Nobody knows what it is there.
What I might say is we have had a podcast with Håkan Westerblad on where he's talked about a lot of this stuff as well. So I might just say if people want to go down that route a little bit more, they can have a look at that. Is it okay if we go back to some questions from Twitter? So Mitch S. Not sure if you know this one or not. I definitely do not. Is muscle glycogen metabolism altered in metabolic states such as type 1 diabetes and type 2 diabetes? So I guess we know that, for example, people with type 2 diabetes tend on average to be not that well trained, and they would use more glycogen during exercise, but because of that. But do you know is there anything specific in terms of their use of glycogen? Do you know, other than
No, I'm not aware of any studies showing that the use they're different in glycogen utilization and non-diabetics, you can say. I mean, the use is actually apparently more the uptake of glucose, which is a limiting factor. With diabetes at rest, but it's I know glucose uptake is normal in people with type 2 diabetes. That's the definition. So I guess not sure either. Another one is Andrew Yoon. Are there any differences in subcellular glycogen use during exercise between males and females? I wonder if that's been looked at. No, but that's a very good question. And again, I can't answer it because it's never been studied, actually. So we want to do that, actually. And that's actually I mean, in general, we don't know that much about the females in exercise physiology, and we don't really know anything about we are actually involved in some studies now with females, but the classic question, is there any difference between males and females? No reason to believe it, but I wouldn't be surprised if there were, actually. So we don't really know, actually.
Yeah, and as you say,
Mm.
more studies need to be done. We've had a couple of people on the podcast as well talking about that. So Abby Smith-Ryan and Kirsty Elliott-Sale. So people can have a look at that as well.
Yeah, right. Yep.
Yeah. All right. So we've got through a fair bit. One thing you said to me before we came on was interesting was, that the fact that when you're storing glycogen, you store it with water versus fat. So we say it's hydrophilic, it likes water. Fat is hydrophobic, so it does not like water. So when you store fat, you don't need to store any water with it, really. Why don't you just tell us what we were chatting about beforehand, how that could be important for people to consider?
Yeah, but that's actually because, we always in sports science often encourage the athletes or even ourselves when we do long-term exercise that we should fill up with glycogen, and after being training, you need to fill up your glycogen depots and so on, because it's going to be a limiting factor eventually. But you can say, is that true actually? Because most Olympic events and so on, they only last 4, 5, 6, 7 minutes or something like that, or even shorter time. So you can say, well, do you really need glycogen, that much glycogen all the time? And there are many positive things with glycogen. It's more efficient. It's you can actually produce ATP at a higher rate. But the downside is actually that glycogen is really heavy to store. That means that every glycogen molecule or either glucose molecule would actually be attached to water, as you say. So it's actually whatever, 3-4 times more heavy than is without water. So you can actually store quite a lot if you count on it. Say you got 400, 500, 600 grams in your muscle all in all. If you actually times that with 3-4, and then you actually have how much it actually weighs in the muscle all in all. So that means you get heavier when you are loaded with glycogen. So we try to calculate how much glycogen is actually needed to set the fuel, you can actually say. And actually, you say if you only exercise for 10 minutes or exercise for 1 minute or something like that, glycogen apparently isn't actually, if you just don't get below this limiting factor, which we believe is 250 millimolar or something like that, that's arguably at least. But we try to manipulate with glycogen. Say with some subjects that's typically not highly trained, but trained subjects, we try to manipulate glycogen, just empty glycogen completely in all body parts, doing exercise in the upper body and lower body, and then actually either fill up as you normally would do completely, or actually fill up to half glycogen. So we managed to do that okay, and then in the same subject, and then there's no effect whatsoever on their 1 minute exercise ability or 10 minutes ability, and they could actually, and maybe more important proof of concept, they could actually lose 0.7 kilo. And if you say that's actually semi-trained, if you're really highly trained, you actually have higher glycogen levels, as we talked before. So we actually lose more weight on that. So the point is actually, if you do some weight-bearing exercise, running, even running uphill or cycling uphill, whatever, then it's important that you can actually lose weight. And if you're running 1500 meters, why should actually losing 1 kilo would actually be quite important for you? Or even more emergent, you can say, where if you are a high jumper, you don't really need that much glycogen. Why don't you lose 1 kilo, right? So so you don't have to fill up glycogen all the time, actually. Athletes know, but it's actually been known. In the intestine, you actually have you can actually lose kilos also if you empty your intestine or have less fibers in the diet and so on. But we don't really know much about the muscle glycogen. So you don't have to fill up all the time. Actually, just be sure that you got enough and not more than enough.
That's a great point. Yeah. So a couple of the podcasts, Javi Gonzalez, Jorgen Jensen. Even the one I'm about to release tomorrow with Jonathan Little talking about keto diets and things, we were saying that, you don't really need to be packing in your carbohydrates every second, like as soon as you finish the exercise, your carbohydrate drinks, your, carbohydrate drinks during the exercise, carbohydrate drinks before exercise, and glycogen loading, because it depends on the event. So as you said, but one thing we hadn't sort of thought about is that body weight. The fact that it's not just not needed, but it may almost be a slight detriment. As you said, like a high jump, imagine a high jumper, if they're a kilo heavier than they need to be.
Right. Yeah.
That's so interesting.
You can start manipulating that. Yeah.
Cool. All right, great. Now, I guess I like to ask people, what else are you excited about, or what are you working on at the moment? So is there something? Oh, you've mentioned a few things, haven't you?
Yeah.
Is there anything else you want to talk about?
But we're still actually working on this localization in the muscle fiber, and actually the mechanisms of it. I would like to go a bit more into it.
Okay.
The mechanism of decreased calcium release and so on, but also we're actually starting now. What was asked from one of the listeners on the male-female differences, which is also quite interesting so far. Yeah. So that's straightforward. You can actually start doing all your experiments all over with the females.
All right.
And then, but I still actually think it's a lot of questions in glycogen. We're not really that more knowledge now than we were 50 years ago. You can say, at least we can say some of the mechanisms. But I think actually still important to look into the mechanisms, but also actually keep this the integrative part of it, because it's a more complex than. I think we actually fool ourselves saying we can isolate things to the the mechanisms at the fiber level or whatever. It's pretty complex also. I just want to highlight the importance of integrative physiology at the whole body level, and combine that with the mechanisms also. So that's what we try to work
Absolutely.
on. Yeah.
Now, one thing I like to ask people sometimes is career challenges. So, it might be if a student's starting out, they might think, oh, every study, you've ever done, works and you get what you expect to get and whatever. Is that the case? Do you normally get what you expect to get? Or are you like me, where I think probably 70% of the time with my studies, I'd end up getting something different to what I thought.
Yeah, but
which can be a good thing as well.
Really broad scientific question, you can say. But, I mean, many times we try. We do the science, at least I do it as well, and colleagues in the field, you can say, try to prove something we believe. But it's in general, the scientific question is that you can never prove anything, but you can actually always try as hard as you want to, as you can say, try to disprove your hypothesis or idea or whatever. So that's the way you should actually work. I actually feel that many, at least in exercise physiology science, they want to prove that something is good or exercise is good or whatever. So really have to disprove it. It's not always easy to do it, I say, but that's the only thing you can do actually. You can't really prove anything. So bear that in mind actually. And another point is actually it's hard. I mean, also stick to some methods you really feel comfortable with, so you really know what numbers you would expect doing different manipulations and so on. Then you can actually expect it, not just relying on some data you've never seen before.
Yep.
So that's my two key points, maybe to do that. And if you need other methods, I mean, of course, you can actually spend time setting up the method, or but then you can also collaborate. I mean, it's, one of the really nice things with the research world is actually that we have competition, but I think in general we have more collaboration than competition. So if anybody wants to collaborate, they are really, and you've got time for it, and it's a good idea, then you would always welcome them.
Absolutely. I think things have become more and more team related. So even I was just thinking, cutting the lawn, you don't always do it yourself. You get someone else, you can go and buy a lawnmower or learn how to do it really well or something. But now we tend to outsource. So, research is like that as well, right? You collaborate with people that are experts in the area, and you can get more done, and pool your resources and all sorts of things. So thank you very much for coming on. But what I'd like to do, if I remember, is to ask you to say a few takeaway messages. So a few takeaways from this chat, 2 or 3 or 4. When you go to a talk, you think, oh, I want them to get 2 or 3 key points that they, pick up.
Right. First of all, you can say, I can answer the question, say, glycogen is important. And then you can say, why is it important? And that's actually, we've got some mechanisms. We know it's actually important for our mechanisms of contracting the muscle, the EC coupling, the calcium release rate and also the excitability. And then another point would be that maybe we should actually not stick so much to average levels of glycogen, taking biopsies or measuring on whole muscles. It's actually very heterogeneous between fiber types, between fibers within the same fiber type, and also within the muscle fiber in different localizations and so on. So put in straight saying glycogen is not just glycogen. There's different kinds of glycogen, which is important. We don't really know how to manipulate with it, but that's an important point also.
Actually, I guess we didn't really talk about the structure of it and the branching of it and things like that. Is the glycogen particles, a bit of talk about that? I guess I'm only thought through it enough.
No, we can do that actually. Yeah. It's stored in particles, and it's stored, and you got loads of particles. But they actually, when you use glycogen, the particles are getting smaller and smaller, and it's actually evenly smaller and smaller, more or less in broad terms. You don't lose one particle and another particle. You're just getting smaller and smaller when you use glycogen, breaking down the glycogen particle and releasing glucose.
Yeah, and is there any evidence that, I don't know, it just occurred to me that, so it's like it's sort of tree-like structure, and as you said, there are a series of glucose that's combined basically. As you're taking off the glucose, does it get harder to actually, as you get less branches and things, does it actually get harder to deplete the glycogen? Like, does it sort of want to hold on to that core, or do we know? I don't know.
But it's difficult to measure things like that. But that's actually one of the, I forgot to mention that before, because it's one of the reasons maybe that you're using a lot of glycogen when you have a lot of glycogen is that the granules are actually large. So you got more endings, you can say, in the branching, and then you can actually use more glycogen. But that's only a hypothesis, you can say, which is there to have.
Yes. All right. Well, thank you.
And that also makes a limit. One of the questions, I guess I think you also talked to Jørgen Wojciechowski about that, is actually when, you use a lot of glycogen, then the granules are getting smaller and smaller. And then when you re-synthesize, they're actually getting bigger. And we know also, that's actually back from the first biopsy studies, that you're actually only getting back to normal, but you actually super compensate. So you're actually getting more glycogen. So that means the granules are actually getting bigger. But where does it actually stop actually? So if you're untrained, you actually stop at one level. If you are trained, you actually get to another level. So what is actually controlling this? Why don't it just get bigger? That's actually one of the key, or one of interesting questions you also have to know actually. So you have it. We have this interesting, it's always nice to find some new designs actually, but we know we have these McArdle patients, and they are actually patients which, that's a very simple disease. They don't have a specific gene encoding for glycogen phosphorylase, muscle glycogen phosphorylase. So they can't use glycogen. They actually bunk all the time, the whole life, you can say. So they can only take up glucose from the blood or use fatty acids. And then also, as you would expect, they only exercise at about, can only at intensities compared to 50% of what you would expect them to do in a person. But they still actually got loads of glycogen. They actually have a lot more than untrained subjects, you can say. So they fill up with glycogen. So you can say, well, what is actually controlling that actually? Why would they have so much glycogen? They never use it actually.
That's a really interesting model, isn't it? Because I know sometimes I was teaching respiration lectures and things, and you'd say, people would say, oh, the hydrogen ion from the lactate is regulating respiration. You say, well, but respiration still goes up in these McArdle patients that don't break down glycogen, so they're not getting lactate and acid.
That's what we call the experiments of human nature, right? So we got a genetic model here, right? So it can be really good to use actually.
Yes, we often use mice, and we knock out the genes, but here you've got some human knockouts. I know you mentioned Jørgen Wojciechowski, and he's got the Inuits that have, some of them have the AMPK. What do they have? Something to do with the AMPK. They've got they don't have it. They're like a sort of naturally occurring knockout. All right. Well, thank you again for coming on. And I'll see you around. I might see you when I'm in Copenhagen in a few months, hopefully.
Yeah, you're welcome. Let me know. Right.
Okay.
Good.
See you,
thanks a lot, Glenn. Nice chatting.
Okay. Good on you. Bye-bye.
Bye.
I hope you enjoyed this podcast. Please like, subscribe, pass it on to your friends and colleagues. Check out the other podcasts. Thanks again.